Welcome to part 6 of Stereochemistry. Here we're going to discuss or begin our discussion with Fischer projections. And Fischer projections are just another way to show chiral molecules. And they're frequently used when drawing sugars / carbohydrates. And this method of drawing chiral molecules was developed by Emil Fischer in the late 19th century. And the reason that reason that he developed this method was because it was much more difficult to print symbols such as dashes and wedges. So instead, Fischer projections depict horizontal and vertical lines, and below is how you interpret those. So let's zoom in. So when dealing with Fischer projections, the intersection of a horizontal and vertical line represents the chiral center. The carbon chain is drawn vertically and in the plane of the paper, with the first carbon of the chain being on top. The horizontal lines represent bonds coming out of the plane of the paper at the viewer, and the vertical lines represent bonds going back through the plane of the paper. So here's an example. Here's a Fischer projection. Here's our chiral center, and we just said that any of our vertical lines really represent groups going away from the viewer, and horizontal lines represent groups coming out at you. So if we were to add this or convert this to dashes and wedges around this chiral center, this is what we would get. See our methyl group going back, this ethyl group going back, our OH and our hydrogen both coming out at us, and we could just convert this structure to our bond line form, and this is what it would look like. To determine the configuration and stereochemistry of Fischer projections, we're going to need to follow the following rules. So the first thing that we need to do is rank our atoms around the chiral center based on priority. Same thing that we've been doing up until this point. And we draw an arrow from priorities 1 to 2 to 3. And now this is very important. If our lowest priority group, 4, is on the vertical bond, i.e. it's going away, then whichever direction, clockwise or counterclockwise, your arrow goes, this is the configuration. So if it's in a vertical bond, it's going away from the viewer, so we can just assign it as R or S. If, however, your lowest priority group is on a horizontal bond, you will need to reverse the answer that you found, because that's saying, like above here, right, our hydrogen is coming out as, that's our lowest priority group, it's coming out at the viewer. So if we were just to assign R or S, we're doing it backwards, we're getting the opposite answer. So let's take a look at the example from above. Okay, so this is our example from above, and so let's assign each of our priorities. So here's our chiral center in red. So we've got, around this chiral center, we've got a carbon, an O, and an H. Well, our highest priority group is going to be the oxygen. This is going to be priority number 1. Our lowest priority group is going to be our hydrogen, that is priority group number 4. And now we have to break the tie. Well, this carbon has a carbon and 2 hydrogens, so HHC. This is a methyl group, so it has 3 H's. So this is going to win. This is going to be priority group 2. And this is going to be priority group 3. And we count from 1 to 2 back to 3. And so that, if we just did that, that would give us R, which is not correct, right? Because our lowest priority group is coming out at us. So we have to reverse our answer. So it's actually going counterclockwise, and therefore this is an S stereocenter. So if we've got multiple chiral centers in a Fischer projection, these are shown as the following. And the configuration of each chiral center can be determined by using the same rules as above. The rules don't change. We can find the stereochemical designation of this carbon or that carbon using those same rules that we just talked about. So let's say we've got two compounds, A and B, and they're drawn in Fischer projections. How would we tell if these compounds are enantiomers or diastereomers? Well, there are two ways that we can do this. The first is that we can take one of these, A or B, and rotate it and see if it is superposable on the other. Now, one thing that is extremely important, if you are going to use this method, Fischer projections can only be rotated 180 degrees, because if you rotate them only 90 degrees, you will reverse the stereocenters, the stereochemistry at each stereocenter. Because remember, vertical bonds mean they're going away from you. Horizontal bonds mean they're coming out at you. So if you were to rotate this 90 degrees, you are going to reverse the stereochemical configuration at each one of those stereocenters. So you can't do that. So what we're going to do here is we're going to take compound B and we're going to rotate it 180 degrees to see if it lines up or superposes on compound A. So I'm going to zoom in here. So we're going to redraw B. We're going to rotate it 180 degrees. And so when we do that, this is going to be at the bottom, and this is going to be at the top. This would be CH3. This would be CH2CH3. And so as we rotate, chlorine's going to be here. That means this is going to be our hydrogen. OH is going to be here. This is going to be your H. So again, we're rotating the whole molecule that way. And so we get this compound. And so let's take a look at how they stack up, A versus B rotated. So if you notice, okay, so there's our CH2CH3, CH2CH3, and if you notice that our Cl and our H are on opposite sides, they will not superpose on one another, and our OH and H are on opposite sides as well. So if we were to overlay these, they would not superpose on one another. So because of that, they are not non-superposable mirror images of one another. A and B are enantiomers. The other way that we can do it, without having to redraw it, is that we can assign each of the stereocenters an RNS designation and then compare it to the other compound, in this case B. If the stereocenters of B are opposite of that of A, they would be enantiomers. If they're mismatched, they would be diastereomers. So let's do that. Let's assign the stereocenter or the stereochemical designation at each of the stereocenters. So we'll start with compound A. So at this stereocenter here, our highest priority group is going to be the chlorine, so this is going to be compound 1. Our lowest is going to be the hydrogen, that would be 4. And then we have to look at a carbon and another carbon. Well, what's attached to this carbon? Well, attached to this carbon is a carbon and 2 hydrogens. Attached to this carbon is a carbon, a hydrogen, and an oxygen. So this carbon wins. This is priority number 2. The oxygen breaks the tie. So this would be 2. This would be 3. So 1, 2, 3. We're going in that direction. Now, the question is our lowest priority group horizontal? Because if it is, that means it's coming out of this, and we need to reverse whatever we get. The answer is it is, right? So we are going in this direction, that is clockwise, but because our lowest priority group is horizontal, that means we have to reverse our answer, so it's really going counterclockwise. So the red stereocenter is S. So now let's do this stereocenter that I'll designate blue. Our highest priority group is going to be the oxygen. Lowest priority group is going to be the hydrogen. And now we're going to have to break the tie between two carbon atoms. This has 3 hydrogens. This has a lot of other things, specifically a chlorine, a hydrogen, and a carbon. So this down here is going to be priority number 2. And this would be 3 up here. So we go 1, 2, 3. We're going in the clockwise direction again. But remember, we have to look. Is our lowest priority group horizontal? It is, right? Here it is. So therefore, we have to reverse whatever direction we were going. So it's not that. It's actually going to be going in this direction, which is S. So in this case, both stereocenters, the blue and the red, are S. So it's SS. So let's now do the same thing for B. We'll designate that as the red stereocenter. Priority number 1 is the oxygen. Priority number 4 is the hydrogen. And here we've got a carbon with 3 hydrogens or a carbon with a chlorine and an H. Well, this carbon is going to win. This carbon only has 3 hydrogens on it, so therefore it is going to be priority number 3. So it's going to be this guy. This carbon here will be priority number 2. This will be number 3. So we go from 1 to 2 to 3. We're going in that direction, which would be counterclockwise. Now, is our lowest priority group horizontal? It is. So therefore, we have to reverse whatever we get for this direction. Therefore, it's actually going clockwise, which would make this R. So the red stereocenter is R. Let's take a look at blue. Our highest priority group is the chlorine. This would be number 1. Lowest priority group is the hydrogen. This would be 4. We've got a carbon here that's attached to another carbon and 2 H's, or this carbon that's attached to a carbon, an oxygen, and a hydrogen. This wins. So this carbon here would be priority number 2. This one would be number 3. So we go 1, 2, 3. We're going counterclockwise. But our lowest priority group is in the plane. So we have to reverse that. So it's not this. It's actually going in that direction. So therefore, we are going clockwise, which would make that R. So in this case, both stereocenters are R. For B, in the case of A, they were both S. So if this is SS and this is RR, they are opposite of one another. And therefore, because of that, compounds A and B are enantiomers of each other. All right. Let's move on and look at cyclic compounds. So rings. So cyclic compounds also contain stereocenters, and when we're dealing with cyclic compounds, substituents can either be drawn as cis or trans, and there are possible enantiomers of each, so that's something to keep in mind. It's imperative, though, when you're examining cyclic compounds, you have got to check for a plane of symmetry, because if a molecule is symmetric, has a plane of symmetry, it's achiral. So always look out for a plane of symmetry. Your eyes are really good at looking at symmetry, so when you see a symmetric, if a molecule looks symmetric, go looking for a plane of symmetry. So here's an example. Here we've got a cyclopentane ring with 2 methyl groups, one up, one down. These guys are going to be trans to one another, right? We've got one on the top, one on the bottom, so they're on opposite sides. They're trans. We've got the mirror image here. So bottom here, top here, it's also trans. These 2 compounds are non-superposable mirror images of one another. Again, don't trust me. build the model. So these guys are going to be enantiomers. Where in the case of the cis isomer, where our two groups are cis to one another, you notice that when you look at this compound, your eyes go to the symmetry. You can see here that this half of the molecule looks like this half of the molecule. And because of that, if I split this ring down the middle with a mirror plane, you can see that we've got this side as the mirror image of this side, and we've got a plane of symmetry. So this molecule is going to be, this ring is achiral, but it does have a stereocenter, right? So we've got a compound that has stereocenters. Those are stereocenters. So if we've got a compound that has stereocenters but is achiral, it's a meso compound. Here are some more examples. In this case, we've got a chlorine and a bromine, and they are on opposite sides of the ring to one another, so they are trans. So we've got our bromine here, its mirror image, chlorine, chlorine. And what these compounds, if you try to superpose them on one another, they would not. They would be non-superposable mirror images. So these guys are enantiomers. We can also look at, in this case, we've got the chlorine and the bromine. They are cis to one another. So here's my bromines. Here's my chlorines. And you notice that because we have two different groups here, there's no plane of symmetry. Even though they're cis to one another, we cannot split this molecule with a plane of symmetry in either of them. Where in the above case, you can see because we had identical groups, that's where the symmetry is coming from. In this case, these compounds are not symmetrical, and they are also not superposable on one another. So these two compounds are non-superposable mirror images, so therefore they are enantiomers. When we're dealing with cyclohexane rings, specifically 1,4 disubstituted, all 1,4 disubstituted cyclohexanes are achiral because we have a plane of symmetry. So if we look here, let's zoom in a little bit. If we look, you can see what's happening is no matter what these groups are, if they're on the 1 and the 4 position, so 1, 2, 3, 4, I can split them right down through the atoms with a plane of symmetry. Same with bromine and CH3, methyl group here. You can see that they are, actually in this case they're trans, they're still split by a plane of symmetry, so no matter what, 1,4 disubstituted cyclohexanes are meso compounds. Now, when we've got cis-trans isomers of 1,3 disubstituted and 1,2 disubstituted cyclopentanes and cyclohexanes, these guys are chiral, so I want to keep that in mind. Cis and trans isomers are chiral. If both substituents, though, are identical, okay, so this is a little bit different. If both substituents are identical, the cis isomer forms a meso compound. So we've got some examples below. Here we've got, in this case, we've got cyclohexane. We've got a bromine and a chlorine. So 1,3 disubstituted. They're on the same side. They're both coming out at you. So in this case, they would be cis. So these two are non-superposable mirror images of one another. In the cyclopentane case, here we've got 1,2 disubstituted. These are trans. These are also enantiomers to one another. So in all of these cases, they are enantiomers. In this case, we've got identical substituents, right? And what I highlighted above is if the groups are identical on 1,3 or 1,4, we're going to form a meso compound. And you can see that I can split this right down the middle here, and this side of the molecule is the mirror image of this side of the molecule. And because we've got that plane of symmetry, this compound then is a meso compound. So as I said before, there are actually compounds out there, atoms out there, that have chiral centers other than carbon, and there are chiral molecules out there that have no chiral centers. So, some examples. So, here we've got silicon. Silicon is right underneath carbon on the periodic table. It can form 4 bonds, and if it's got 4 different things attached to it, so here R1, R2, R3, and R4, they're all different. These compounds are chiral. Germanium is the same way. It can also form 4 bonds, and we can in a tetrahedral geometry, so we can get 4 different things on there. You can have chiral. This could be a chiral center if all of these are different compounds. Nitrogen as well. So not your standard amines, but a quaternary ammonium salt. So that means when nitrogen forms 4 bonds, it's not an amine anymore. It has a positive charge, so it's an ammonium. So this would be, and it's charged. So this would be an ammonium salt. It's a quaternary ammonium salt, and again, it's got 4 different things attached to it, and it's tetrahedral in geometry. So this would be chiral. Sulfur compounds are also chiral. In this one, you may be able to say, well, wait a minute. There's only 3 different groups on there. We got an oxygen R1 and R2. Well, in this case, the lone pair of the sulfur also is considered a group, and these are also chiral, these chiral sulfoxides. Now we can also have chiral molecules that have no chiral centers, and we talked earlier on the first slide in part 1 about DNA. DNA doesn't have chiral centers, but it has a twist to it, it has a handedness to it, just like a screw does. But that makes the molecule chiral, so it is not superposable on its mirror image. Other examples of molecules that don't have a chiral center but are chiral because of their twist or their conformation would be this compound shown here. This is called binap, which is 2,2' bis diphenyl phosphino 1,1' binaphthyl. Say that 3 times fast. But these 2 compounds, these are the S and the R conformation. They differ through the twist through this carbon-carbon single bond. So they are non-superposable mirror images of one another. Other examples are single-walled chiral nanotubes. So here you can see these are all carbon atoms, and these guys have a twist to them. If you look down the barrel, you can see how the tube is actually twisted. And what that means is that because it has that handedness, that twist to it, just like DNA, it is not superposable on its mirror image, and therefore is chiral.